It is a beautiful morning. It is 8:23 a.m. It is November 9th, and we are going to do some calculus. We're going to continue the 2012 AP Calculus AB exam. We are going to start section 2, part A. This is the free response section. All right, we get a calculator. College Board put out this exam a decade ago. We're going to do free response question 1. And two quick things. Subscribe to the channel, okay? That's how you get notifications. That helps you. And like the video, okay? That helps me. And while you're ringing that bell down there, in the comments, let me know if you want to see a certain test. I will take requests. And as far as requests go, I've been asked what calculators I use. I use the TI 84 Plus CE, the one with the colored graphs, how you can pick different colors for different graphs. There are an entire slew of colors, and I put the links in the description below for any of those colors. They're kind of cool. I like them. My personal one is the mint green. I do have the mint green one. I just love the color green. All right, and other than that, hey man, let's get started. 1 reads ho tables. It doesn't read that. I just get excited when I see tables. 1 reads, the temperature of water in a tub at time t is modeled by a strictly increasing twice differentiable function w, where w of t is measured in degrees Fahrenheit and t is measured in minutes. At time t equals 0, the temperature of the water is 55 degrees Fahrenheit. The water is heated for 30 minutes, beginning at time 0. Values of Wt at selected times t for the first 20 minutes are given in the table above. That seems like a lot to read. A asks or tells us, use the data in the table to estimate. That's a big word here. W prime of 12. Show the computations that lead to your answer. Using correct units, interpret the meaning of your answer in context of this problem. Okay, let's start with the first thing. Estimate W prime of 12. W prime is derivative, which is the same thing as slope, right at a time of 12. We don't have 12. 12 would be right there. So what do we do if we're estimating it? We take the 2 closest points, 9 and 15, and I just do a change in y over change in x. Okay, so I'm literally going to say x1, y1, x2, y2. So 67.9 minus 61.8 all over 15 minus 9. And guess what? All right, it's a calculator problem. Get out that TI 84 Plus CE. Now, I'll do this so we can see the fraction in the background. Turn this bad boy on. And anytime I have a fraction, alpha y equals enter. All right? I'm just going to use that function, alpha y equals, so I don't got to use parentheses for the top or bottom. Makes it a lot easier. 67.9 minus 61.8 all over 15 minus 9. I get 1.0166666. I am going to round. Notice that a lot of my answers in multiple choice, if they're decimal, will go 3 decimal places. So I'm going to call that 1.017. I could say 67. And if you're going to ask me, well, how do I know what to round to? As long as you're accurate with your rounding, okay? I always keep it 3 if I have to, because that's how all the multiple choice questions are. Okay, so I'm going to call it, this will round up to a 7 because the number after it is 5 or bigger. So I'll go back here, say 1.017. All right, now they want us to estimate that. Show the computation that leads to your answer using correct units. Okay, using correct units. So I'm going to put them on the label right here. This is a rate. It is degrees Fahrenheit per minute. Okay, so it's degrees Fahrenheit per minute. Okay, now they also say in the second part, using correct units, interpret the meaning of your answer in the context of this problem. Okay, so what does this mean? Okay, so I'm going to go here, here, and we'll do this with some, like I'm doing it in pencil, a nice gray. And I will say the temperature of the water, okay? The temperature of the water is increasing at 1.017 degrees Fahrenheit per minute. There's our appropriate labels. Right at T equal 12, okay, or right at minute 12. There you go. That's in the context of the problem. It speaks of the temperature of the water, the time, and the rate is increasing. That's a positive 1.017. Okay? There you go. I thought that was a pretty simple 1A. 1B states, use the data in the table to evaluate the integral from 0 to 20 of w prime of t dt. Using correct units, there it is again, interpret the meaning of the integral from 0 to 20 of w prime t dt in the context of this problem. All right, let's get going. I don't think we're going to need a calculator for this problem, but hey, you never know. Using the data on the table, I put the table back up here. The integral, okay, now here's what you need to keep in mind. You're going to say to yourself, are they asking us to do an LRAM, RM? We don't have to do such things. They're asking us for the integration of the derivative of W. Remember, we have W, we have the derivative, and we have the second derivative, okay? These are all one derivative away from each other. They're giving us this. If we integrate it, we are going backward, aren't we? So we're figuring this out. That's what they give us W of t up here, okay? So when I take the integral with bounds of something, okay, I got to go back. So I go from the derivative to the original, putting in the upper bound, minus the original, putting in the lower bound. That's what you got to understand, right? They gave us this. In our integral, putting the bounds will go into the original. All right, well, I know what W of 20 is. It's 71. I know what W of 0 is. It's 55. Now, I said you don't have to use a calculator. If you want to check that, you can, but the answer is 16. Okay? And if my rate is in degrees Fahrenheit per minute, my original equation is just in degrees Fahrenheit. Remember, I'm going back. Okay? I'm going back to the original label. So 16 degrees Fahrenheit. That's the answer to this right here. That's the first part. Now, the second part is using correct units. Using correct units, we'll change up the colors. Interpret the meaning of that number in the context of the problem. All right, well, again, I had a rate, and I went back to just the initial label. So 16 degrees Fahrenheit from time 0 to time 20. Remember, that's the total. When we integrate, we're adding up the total. That's why they're called Riemann's sums. Okay? So, the water temperature, because we're just talking about the temperature, it's not the rate anymore, changed or increased, because remember it was strictly increasing, a total of 16, oh, that's 16, sorry, but oh my, I'm not gonna, that's terrible, 16 degrees Fahrenheit from time equals 0 to time equals 20, and we'll put minutes right here. This is the explanation of this answer in the context of the problem. The water temperature changed or increased a total. Because remember, we're totaling. That's what integration does. A total of 16 degrees Fahrenheit from time 0 to time 20. 1A is done. 1B is done. 1C. For the interval from 0 to 20 inclusive of time, the average temperature of the water in the tub is 1/20th times the integration from 0 to 20 of Wt dt. Use a Riemann's sum. Oh, I like when you talk dirty to me like this. Use a Riemann sum with the 4 subintervals indicated by the data in the table above to approximate that. Does this approximation overestimate or underestimate the average temperature of the water in those 20 minutes? Explain your reasoning. A lot of explaining in part 1. By the way, did I mention that it's a left Riemann sum? So we're going to use an LRAM here with the 4 subintervals they gave us. Let's take a look at this, and this is where I love to color coordinate. Now, this 1/20th is going to stay the same. So I'm going to take 1/20th times. This integration right here is where I'm going to do the LRAM. So my LRAM is going to be whatever values are in here. Hopefully that's enough space. If not, I'll have to extend those parentheses. Now, my first subinterval goes from 0 to 4. This is subinterval 1. Okay? Since I'm using LRAM, I look at my y values and I take the left one, 55. But I got to multiply that times my width. My width is 4. Plus, subinterval 2 goes from 4 to 9. That has a width of 5. And I got to look at my left y value, 57.1 or 61.8. This is the left one. So I take my width, 5, and multiply it by 57.1. Plus, oh, I got 2 more, so yeah, I'm definitely going to have to do that. Plus, let's go orange here. 9 to 15 is my next subinterval. Because remember, it says we have 4. That's subinterval 3. That has a width of 6. So I take 6 times my left value. Out of these two, 61.8 is my left value. Plus, and yeah, the gray always comes back. Purple. Let's stay colorful. 15 to 20 is my next subinterval. That has, subinterval 4, a width of 5. 5 times, out of these two, my left value is the 67.9. Okay? So remember, there it is. I'm going to put all that in a calculator. I don't care what anybody says. It's a lot to do mentally. I mean, it could be done, but there's a reason they let us use a calculator here. So turn this on. Alpha y equals anytime I have a fraction. 1 over 20 times 4 times 55 plus 5 times 57.1 plus 6 times 61.8 plus 5 times 67.9. And I got to put the, wow, look at all that red. I still got to put my closing parenthesis for the 1/20th. And I end up with 60.79, okay, equals 60.79. All right? Again, an integral is we're adding up. We're adding up just the W's, which is degree Fahrenheit. Degrees Fahrenheit. Okay, but what is this? This is the average temperature. The average temperature. So does this approximation, does it ask us to explain our reasoning? Okay, they want us to answer that, and we did. The answer to this is this right here. Okay, it doesn't say explain in the context of the problem what the solution is. It just asks us, is this approximation, this 60.79, is it an overestimate or an underestimate? Remember, hey, when we first started this problem, and it said that this is strictly increasing. All right, that means, okay, if I were to graph this, yes, I can plot those points or whatever. If I were to graph this, this would be a strictly increasing function, okay? And we have 4 subintervals, 1, 2, 3, 4. Let's do our little 4 subintervals here, but they're left ram. The left corner needs a touch. Subinterval 1. The left corner of subinterval 2 needs a touch. The left corner of subinterval 3 needs a touch. And the left corner of subinterval 4 needs a touch. Now, if I'm trying to find the area under the curve of all this, okay, the total area underneath that curve is everything underneath the curve, right? But if I'm using LRAM and I'm adding up just the areas of these rectangles, that means I'm just adding up the area of this rectangle, and this rectangle, and this rectangle, and this rectangle. And you'll see the light blue that's left, we're not counting that. So the areas of those rectangles are actually going to be less. Okay, it's going to be an underestimate. We are going to have less than the actual area under the curve. Right? But they want us to explain our reasoning. So first, let's make the statement. Let's declare our intent that this is an underestimate. Explain. Comma. Let's do comma. Since we used LRAM, or you can say a left Riemann sum, which is the words they used, a left Riemann sum, on a strictly increasing function. That explains exactly why. Now, if that function would have been decreasing, that would be a different story, but it states that it's strictly increasing. All right? 1C, done. The last part of free response question 1, 1D, as in done. For the t-value of minutes between 20 and 25 inclusive, okay, the function W that models the water temperature has a first derivative given by W prime of t, which equals 0.4 times the square root of t times the cosine of 0.06 t. Yeah, that's going to be a calculated problem. Based on the model here, what is the temperature of the water at time 25? Okay, so basically, they're saying, all right, let's do this. At time 25, what is this temperature? So we want to find out what value would be right here. Okay, it's established. They give us W prime. Okay, here's what may or may not be so obvious. They give us W prime, yet we got to find W of 25. And then they give us this kind of this interval, or let's refer to those as bounds. I know if I integrate derivative, that would end up giving me the original W. I know I have bounds, 20 to 25, and I even know that when I have bounds, it's the upper bound in the original minus the lower bound in the original. Even better, my friends, even better, I have values I can put in here. What do you mean, Visca? I'll show you. W prime is this equation here. So let's go ahead and put that in. All right, let's put right here. We're going to do the integration from 20 to 25 of that equation, 0.4 square root of t times the cosine of 0.06 t dt. Okay, that's all in right here. That's my W of t. That's one of the values. That's only one. All right, equals, this is what I'm trying to find, so I don't have a value for that. W of 25 minus, oh Lord, I have this. W of 20 is 71. It's on the table. Okay? So all I'm going to do, okay, is I'm going to add 71 to both sides. And that will isolate my W of 25, which is what I'm trying to find. That's going to be 71 plus the integration, okay, of 20, from 20 to 25, of W prime of t. And I could write W prime of t here if I want, and I could write it again here, but let's write what we're going to put in the calculator. That would make me feel a little bit more toasty and cozy. I'm literally going to put this in the calculator and hit enter. And that wonderful TI 84 plus CE calculator, where the links are below. Oh, a shameless plug. That's terrible. Okay, so let's turn this on. And I'm going to have 71 plus math 9. My lower bound is 20. My upper bound is 25. Okay, 0.4 times the square root of x. We're using x instead of t. Pop out from underneath the square root cosine of 0.06 x, parenthesis. Okay, I have two opening parentheses, so I should have two closing parentheses, and I do. Okay, dx. And I just hit enter. And I get 73.043. Did I do that right? Why do I get 0.3? Yeah, that is right. So I've got 73.043. And since it's a W, it's not a rate, it's just degrees Fahrenheit. Let's make sure they didn't ask us to explain anything, because based on the model, what's the temperature at time 25? That's it. It is, yeah, 73.043 degrees Fahrenheit. Wow, look at us go. That wasn't all that bad. 23 minutes. 23 minutes. All right. Again, thank you for being here. I always appreciate it. And please, please, please subscribe, because that's how you see when I put up free response question 2. And like the video, because that helps me. And man, I want to hear from you guys. Throw in some comments. I had them locked before. They're not locked anymore. Boom. Oh, by the way, I put up a how to solve a Rubik's Cube video because all my students were asking about it. It's super sweet. It's super sweet. I suggest you check that out too. That's awesome. I know how to solve a Rubik's Cube, and kids just, they want to learn the minute I show them. Okay, so I will see you later, hopefully for free response question 2. Bye-bye.